Welcome to the Explainer. Today we are cracking open one of the Internet's most important and maybe most underappreciated documents, RFC 791. This is literally the rulebook that defines how data gets from one place to another online.
So here's how we're going to break it down. We'll start with this idea of a digital postcard. Then we'll look at the huge problem that all of this was designed to solve. We'll get into the two main jobs that the Internet Protocol does, take a peek inside the postcard itself, and then we'll get to the most surprising part, how this whole system is, by design, completely unreliable.
All right, let's just jump right in. Go back to 1981. The folks writing this document had what sounds like a simple problem, but it was massive. How do you get a block of data from one computer to another when those computers are on totally different networks? They called this whole mess an interconnected system of networks, or a catenet.
And the brilliant solution they came up with was this thing called a datagram. The key here is that it's completely self-contained and independent. It's just like a postcard you drop in a mailbox. It has the full destination address and the return address written right on it. You don't need to call ahead or set up a special delivery. You just send it. The postcard has everything it needs to get there all on its own.
And that brings us to the core challenge they were facing. This catenet. It was a real Wild West, a whole universe of different networks built by different people with different rules. None of them were designed to talk to each other.
So the big question was this: if every network speaks its own language, how do you create a universal translator? You can't possibly expect an application on your computer to know the specific rules for every single network it might have to cross to send a message. That would be an absolute nightmare. It would be impossible to keep up.
The solution was genius in its simplicity. They created a new layer that sits right in the middle of everything. You've got your applications, like your web browser, at the top. You've got the actual physical network stuff at the bottom. And right in between, they slotted in the Internet Protocol, or IP. It acts as that universal translator, bridging the gap between everything.
So how does this middleman, this Internet Protocol, actually pull it off? Well, it turns out its genius lies in two basic but incredibly powerful functions. Think of them as its two superpowers.
And here they are. First, addressing, which answers the simple question, where is it? It gives every single device a unique address so the datagrams know where to go. Second, fragmentation. This one answers the question, will it fit? It's a way to break big messages into smaller pieces so they can squeeze through networks that have size limits. That's it. Everything the Internet Protocol does boils down to these two fundamental jobs.
Now, let's get specific about addressing. The RFC makes a really important distinction here. There's a name, like a website name. There's an address, which is the specific number for that computer. And there's a route, which is the path to get there. The Internet Protocol is laser-focused. It only cares about the address. It doesn't know about names, and it doesn't pick the route. Its entire job is to get that postcard to the right mailbox number.
Okay, so IP knows where to send the postcard. But what happens if, along the way, that postcard is just too big to fit through one of the mail slots? This is where that second superpower comes in, fragmentation.
IP doesn't freak out. It just chops it up. So in this example, you've got a 472 octet datagram. An octet is basically a byte, and it hits a network that can only handle 280. No problem. IP slices it into smaller pieces called fragments. It gives them all the same ID number, so the receiver knows they're part of the same original message. Then, it uses a couple of flags. The more fragments flag is like saying page 1 of 2, and the fragment offset tells the receiver exactly where this piece fits in the puzzle. The very last piece has that more fragments flag turned off, which is the signal for, okay, that's everything. Then, the computer on the other end can put it all back together perfectly.
So, we've talked about addresses and fragmentation instructions and all this other stuff, but where does all this information actually live? Well, it's all packed neatly inside the IP header.
And here it is. This is basically the control panel for every single one of those digital postcards. It's a tiny 20-byte block of data that's attached to every packet, and it contains all the essential instructions for delivery. This is based on the actual diagram from that original 1981 document.
First up, the most important fields, of course, the source and destination addresses. These are the 32-bit to and from addresses on our digital postcard. Without these, absolutely nothing would work.
Next, we've got the fragmentation controls we just talked about. See these flags and the fragment offset fields? That's the instruction manual. This is what tells the receiver, hey, there are more pieces coming, and here's exactly where this piece goes. And this part is just brilliant. It's called time to live, or TTL. Think of it as a self-destruct timer. Every time a packet goes through a router, this number ticks down by 1. If it ever hits 0, the packet is just deleted. This is a critical safeguard that stops lost packets from bouncing around the internet forever, clogging everything up.
So, for all this cleverness with addressing and fragmentation, the Internet Protocol has a dirty little secret. And honestly, it's the most surprising feature of all. And it's all about what IP doesn't do.
Get this. IP makes 0 guarantees. It doesn't confirm that your data was delivered. It doesn't check if the data got messed up along the way. It won't resend anything that gets lost. It doesn't even make sure the pieces arrive in the right order. It is truly a best effort system. It just throws the postcard out there and hopes for the best.
And this wasn't some oversight. The original document says it, plain as day. It does not provide a reliable communication facility. This unreliability is a feature, not a bug. By keeping IP simple, stripped down, and fast, it pushes the hard work of making sure everything is reliable up to other protocols that sit on top of it.
And that leaves us with a huge question, right? If the absolute foundation of the internet is this unreliable system that just kind of hopes for the best, how are you even streaming this right now? How does your email get there? How does any of it actually work? Well, that just shows you the genius of a layered system. And it's a story for